Okay, so in this video we're going to look at projections, both vector and scalar projections. Scalar projections you'll see mainly at the high school level, but vector projections are the really important ones. In a university course like linear algebra, vector projections are a really central topic, and it's super important to have a deep conceptual understanding of these things, not just to be able to compute them, right? There's several ways of looking at these things. We're going to look at them from different angles and perspectives, and see why we're interested in these things, what they're used for, what they kind of represent. And I really can't stress enough that it's important to actually have this deep conceptual understanding of these things. So many students will just learn how to compute a projection and then kind of think that they're fine on the test, and that's not enough. You need to have an understanding, a deep understanding, in order to be able to solve problems involving these things. So that's what we're going to do in this video, is really understand what projections are. So, okay. So first of all, what is the idea behind projections? You've probably seen something like this, where they say, okay, the projection of a vector A onto a vector B is what happens when I go from the tip of A and draw a line down to B at a right angle. So I get this line segment that connects A to B at a right angle. And this is absolutely correct. What we do is then, well, that's a little bit bigger than I intended. Here we go. We go along B to that point, and we take this piece of B, right? This bit of B, and call that. This is what's called the vector projection. In university, they'll just say the projection, and then they mean the vector projection. If you're thinking about the high school parlance, the difference between vector and scalar projection. We'll see what scalar projections are in just a few minutes. But if you hear them say the projection, they mean this, the vector projection. And so this thing right here, this thing is what we call this vector, right? Is the projection of A onto B. And I'm going to highlight to draw attention to this, the A in its color, the pink there, and then the B in maybe its color green, although it's a slightly different green. Because you may have thought, wait a second, you said the projection of A onto B, and then I wrote the B first. And this notation often confuses people. So why is when I say the projection of A onto B, why do I have the B down here and then the A in the brackets? Well, the idea is that we can, and this is how you remember it. We want to think of this as a function of A. So we want to think of the projection onto B as a function that can take in a variable x. It takes in a variable x and then spits out a vector, which is the projection of that vector x onto B. And so that's why the B goes down here as sort of part of the function notation, and then the x is what comes into the brackets. So when we talk about the projection of A onto B, this is the projection onto B function having been applied to A, and that gives us this vector. That gives us this piece of B, and the idea intuitively, and this is a really important thing, is that this vector. It represents two things. So it's supposed to be measuring the amount that A goes in the B direction. It's sometimes called the the component of A in the direction of B. And if this seems familiar to you, it's because it should be. If I have a vector, we'll call this C, which is C1, C2. This is in two dimensions. It has an x coordinate C1, or x component, and I drew C1 way off. Hold on 1 second. Here we go. This is C1, its x component, and C2, its y component. And so I can think about or coordinate, but you might have heard this term, the x component or the y component, and that is telling me the x component is telling me how far this vector goes, how much in the x direction this goes. And then the y component is telling me how much in the y direction this goes. And as I'm saying this, I'm realizing I should probably label the axes if I'm going to talk about them as the x and y axes. But the idea behind projections is that we can do the same thing for any vector, right? We can, and these arrows here, this green arrow is what we call the projection of the vector c onto the x-axis tells me how much in the x direction it goes. And this pink arrow going up from the origin to C2, this is the component of the vector in the y direction, or the projection of this vector in the y direction. And we can see also that we could obtain these by connecting the going from the tip of that vector c to the x or y axis at a right angle, making a right angle, and then taking that much of the x or y axis. So that's the first thing to note, right? Is that this is kind of a generalization of that. We're thinking, okay, we want to be able to, in the same way that we can measure how much any vector goes on the x or y in the x direction or the y direction by projecting it onto the x or y axis, I want to be able to do that with any vector, right? So if I have b here, I want to be able to say how much in the b direction does a go. The same way I can ask how much in the x or y direction does b go, or does a go. That's what the projection of a onto b is. It's the component of a in the b direction. How much in the direction of b does a go? Second thing to note, and you might have noticed this from the picture already, is that if you recall what our vector addition definition is, you'll see that regardless of which order you do it in, the vector c is actually the sum. It's the sum of its projections onto the x and y coordinates, right? It's the projection onto the x coordinate of c plus the projection onto the x-axis of c plus the projection of c onto the y-axis, right? In order to get to the point c, we go however far it went in the x direction and however far it went in the y direction. We can decompose c into its projections onto the coordinate axes, and we're going to see pretty soon that we can do the same thing. We can decompose any vector a into the sum of its projection onto another vector b and the what we have right here. So this vector, a vector, and this is going to be a key to figuring out the formula for the projection of a onto b, is that we're noticing that we have this vector here, which is orthogonal to b. It is at a right angle to b. So the same way that the projection of this vector c onto the x-axis, right, this was orthogonal, was perpendicular to the projection of c onto the y-axis, and so we could decompose it into the sum of these two orthogonal vectors. The same way we can decompose a into its projection onto b plus this vector here, which is orthogonal to that projection. So you might hear this called the orthogonal projection of a onto b. This is a term that you might be hearing, and this is where that comes from. Is the idea that it allows you to decompose a into orthogonal vectors. And it turns out you can actually always do this. You can always do this with any vector. And I don't want to get into this too much in this video because it's very deep, very rich, very nice topic, and we'll do lots and lots of videos on this. But for now, these are the sort of the two out of the three ways that I want to get us thinking about projections. The last one is that I want us to think about, and this is another very interesting way of looking at this, and we'll probably do an entire video on this. We want to think about the projection of a onto b as the closest point on b to a. So, and the way to think about this is, and I don't want to use that color because it doesn't show up very nicely. What do I want to use? Let's just do this. I want to think about if I were to try to connect a to b via a line segment, right? If I were to draw a vector connecting the tip of a to b on any point of b, wherever I could do this, out of all of those, what is the shortest vector? What is the vector with the smallest magnitude? What is the shortest distance between a and a point on b? And this, as you might have guessed, is going to be the projection, right? If I take a and I connect it to b in the shortest possible way, the way that gives me the shortest possible vector, right? I'm thinking about, out of all the points on b, which one is the closest to the tip of the vector a, to the point determined by a. Well, if I take that point and then I connect that to the origin, it gives me it gives me the vector projection of A onto B. And we will go into this in depth in another video. But I really encourage you all to think before you watch that about what is the relationship between the orthogonal aspect of this vector and the fact that it's the closest one, right? What is that relationship? Why is the closest one, the closest point on B to the tip of A, the one which, when you connect it to A, is going to give you this vector which is orthogonal, which is going to give this vector which is orthogonal to B, right? The vector connecting A to B is going to be orthogonal to B if you construct that vector by connecting the tip of A to the closest point to it on B. So those are the three main ways we want to think about these things. And that's just great. I know you're saying, but how do we actually compute this, right? I got here because I needed to compute for a problem the projection of a vector onto another vector. And one of the reasons I go into this much depth is because you could just go and look that up, right? There's a formula online, and so there's not really much point in me just showing you the formula. The whole idea behind deriving the formula is that it gives you some understanding that you wouldn't get otherwise. And also, and I harp on about this ad nauseum in these videos, but it's really, really true. The way that you get the best marks, the way that you get the best learning experience as well, is by really understanding these things on a deep level. This is the biggest job, I think, of a teacher. At least I consider it my primary responsibility as a TA, to convince students of this, to convince them that they have to get out of this high school mentality where you just memorize things and get formula sheets, because that, it just doesn't work in university. The tests are designed to precisely to stop you from doing that, so that you won't be able to pass if you try to do that. Every professor I've worked for has taken pains to design these tests. So that you will have to understand, to test your understanding, not your ability to memorize things. So that's the second reason that we're and just in case you were getting frustrated and be like, well, you just show me the stupid formula. You could have gotten that from like Google Images. We're going into depth here for a reason. This is how you really understand and succeed in university math. Okay, enough blathering. Let's get to it. Eventually, we do have to actually derive the formula. We can't just talk all day. So suppose I now want to figure out. It's like, that's great. I now know what is the point of these things. I can think about them conceptually. That's very nice. But what if I actually need to figure out what this thing is? I actually need to come up with a formula. Someone asks me to find the vector. I need to use it for something. Well, let's not delete the axes. How do I do that? How do I find this projection? Well, the observation that is going to allow me to find the projection of A onto B is actually what I was just talking about. The fact that they are orthogonal. That is one of the two. And that, of course, means that the dot product is 0. If that seems weird, please do go and check out the videos on the dot product and the cosine rule and everything, and orthogonality. But the second observation that allows me to do this is, and I want to do this in this color, sure, to match the arrow, is that the projection of A onto B. This is a scalar multiple of B, right? It's some amount along the B vector, right? And we know from our definition of scalar multiplication of vectors that this takes me some amount in the B direction, or if it was a negative number, if C was negative, it would take me some amount in the opposite B direction. But it's somewhere. I stop somewhere on the line spanned by B. And that gives me the projection of A onto B. And so I know, let me come back up here and use go back to my purple. I know that the projection of A onto B is C times B for some scalar C. And I need to figure out what that C is in order to figure out the formula for this projection. And how do I do that? Well, I note that as we already saw, or as I already mentioned, the projection of A onto B, so C times B, this projection is perpendicular to this vector. And what is that vector? What is this vector here? This vector here this is, if we remember our definition of vector subtraction, what if I were to take the vector, the projection of A onto B, this C times B, and I were to subtract it. I were to subtract it from A. Well, that means that I place its tail at the tip of A, and then I draw it in the opposite direction from the one that it goes, as I've drawn it out from the origin there. And then I connect the origin to that point, and I get this vector. This vector, this is A minus CB, or A minus the projection of A onto B. And this vector is perpendicular to the projection of A onto B, this C times B, right? It is orthogonal to this. So that means that their dot product is going to be equal to 0. And this is what allows me, and again, and this is one of the first things I ever mentioned about vectors, was just point this out, that these are in fact the same vector, right? Those two vectors, even though one is shifted over, it's shifted along the vector CB, right? I shifted it from here to there. These are still the same vector, right? A vector is determined uniquely by its magnitude and direction, and this is why I stressed this in the first video where we looked at vectors. Because that these are just different representations of the same vector. This is the same vector, and it's been moved, is precisely to obviate confusion like this. About, wait a second, you said that's the vector, but actually now it's over here. What is going on? These are different vectors. This is one of those subtleties, the distinction between vectors and points. This is the same vector. And if there's anything at all confusing about this, please do look at the intro to vectors video. Okay, so I know that C times B is perpendicular. The projection of A onto B is perpendicular to this vector over here, which is A minus C times B. And this is the relationship which is going to allow me to solve for the C, to figure out. And once I determine the C, right, I determine what the projection of A onto B is, because it tells me how much along B I go. And C, by the way, C is what we call the scalar projection. Scalar projection, right? It is the scalar that tells me how far along B I go in whichever direction, forward or backward, in order to find the vector projection. That is the relationship between these two things. And like I said, they don't really talk about that at the university level, mainly in high school. So the fact that these two vectors here are orthogonal, C times B, the projection of A onto B is orthogonal to A minus C times B, A minus the projection, means that CB dot product with A minus C times B is equal to 0. And for my dot product properties, I can distribute this in and say this is C times B dot A minus C times B dot C times B is equal to 0, if and only if, and I'll move this over and bring that C out and say this is C times B dot A minus C squared times B dot B. And again, if you're wondering about why we can do this with dot products, I can just pull that C out like this. Please do check out the video on dot products for the dot product properties, the way we can do arithmetic with dot products. And so last thing is we get C times B dot A is equal to C squared times B dot B. But what is B dot B? It is the magnitude of B squared. So finally, B dot A, C is what I'm trying to solve for here. Rather, C is, after I'm going to divide both sides, I'm going to divide both sides by C times B, magnitude of B squared, and get C is equal to A dot B, because that's equal to, it's the same as B dot A, and this is the way that they typically write it in this order. I don't want to confuse people. And also they put in the denominator magnitude of B squared. C, and this is it, C is equal to A dot B divided by the magnitude of B squared. So that's the scalar projection. What does this mean for the vector projection? It means that the vector projection of A onto B is C times B, which is going to be A dot B over the magnitude of B. I keep writing A for some reason. Magnitude of B squared times B. And I put these exterior brackets here for a reason, and that is to emphasize, because this is something that trips people up. I really want to emphasize that A dot that this is a scalar, right? That A dot B over magnitude of B squared is a scalar. That we compute this first, right? This is a real number, and then we multiply it by the vector B. Because a lot of people will say, okay, this is actually just A. You say, why is it just A? Well, this is A dot B over magnitude of B squared dot product with B, which is A dot B over magnitude of B squared, which is A times magnitude of B squared, because they group the B's like this, over magnitude of B squared, which is A, after they cancel this, right? And this is wrong. This is not, that is not it, right? There's a few things wrong with this. One is that here, this is not the dot product that we're taking. This is multiplication, right? Not dot product. This is a number, and we're multiplying it by a vector. And the second thing is that if we got to here, right, then we would be taking A dot B, and B dot B would be a scalar, and then we couldn't take the dot product of a scalar with this vector A. So that's not it. But this is a common mistake. This and this thing up here, this and this thing there, where we screw up the order, the B and the A, right? Those are the two main sort of notational things, or things that people do wrong when they write this. So I just wanted to emphasize that because this causes people a lot of problems. Okay, so that's it. That's I think this is a good place to end, because we've derived our formula, and let me just, in all its glory, put it down here once and for all. The projection onto B of A is A dot B over the magnitude of B squared times B. And I'm going to stop the video here because it's getting a little bit long. But like I said, there's a lot more to this. There's a whole playlist on projections and things we can do with these. We get into the Graham-Schmidt process and all sorts of great stuff like that. So please do check that out, because it's like I said, it's just a really core topic in linear algebra, and you need to have a really solid understanding of it, not just how to compute the thing.